Efficiency is the ability to do something or produce something without wasting materials, time, or energy. How does that work? Well, watch this. Here is just a hypothetical machine. It is a made-up machine. The purpose of any machine is simply to make work easier to do. You put work into a machine. There's some work going into this machine. The work goes into the machine. It might be a handle that you squeeze or push, such as with a pair of scissors. Sure, a pair of scissors is a machine. It might be electricity going into something, say, like a sewing machine. Sewing machine is a machine. How does it operate? Well, you plug it in, electric current causes a motor to run, and the motor does work. That energy, that electricity, is the work that goes into the machine. Remember, of course, that work is energy. So if I say work in, I also mean energy in. So you put work into any machine. It makes no difference what the machine is. It makes no difference how complicated the machine is. It makes no difference how simple the machine is. Every machine does one thing. It's supposed to make work easier to do. And you have to put energy or work into a machine to get something out of it. Well, what do you get out of it? Well, you get useful work out. You know, if you use a pair of scissors, you put work or energy into that pair of scissors by squeezing the handle of the scissors, and you get some useful work out. You cut a piece of paper. Well, if you notice here, the work in is a lot bigger than the useful work out, represented by the sizes of the arrows. You can see that. The work in arrow is a lot bigger than the useful work out arrow. So some work or energy is lost by the machine. Well, where does that energy go? That energy goes to heat. The machine produces heat. If you squeeze a pair of scissors, you may not feel it, but that actually doesn't just cut the paper. It actually increases the temperature of that piece of paper where you're cutting it. Not a whole bunch. Only an imperceptible amount of heat energy is released to that paper when you use that pair of scissors. Now, if you're talking about a car engine being a machine, you can certainly understand that that car engine gives up some heat energy, because you can feel the heat energy in a car engine. It's hot after it's been running a while. So some of the energy that could do work in any machine is lost due to waste heat. Now, to go back to the pair of scissors for a second. If you cut a piece of paper with a pair of scissors, you hear a sound when the paper is cut. So one of the forms of energy that comes out is also sound. And if you were to add up the useful work and the heat and the sound, they would be exactly equal to the work that was put in to this machine. It's called the law of conservation of energy. Energy is never created, it's never destroyed. It simply changes form. You do some work in, that represents energy. Remember, work is energy. So you do some work that goes into the machine. That work and that energy comes out as either useful work or wasted heat and wasted sound. But when you add it all up, nothing is destroyed, nothing is really lost. It simply changes form. We took this work and this energy and we turned it into heat, sound, and useful work, and they are exactly equal to each other. The work done on the machine equals the energy and the work that comes out of the machine. So we have to ask ourselves, why is it that a machine, such as our hypothetical imaginary machine here, produces waste heat and waste sound that we're not really going to use? Why is it that this machine wastes some of the energy? And the answer is actually very simple. It's right in front of you. It's understood. Even if you don't think you understand it, you do. Why does the pair of scissors produce heat? And why does it make a sound when you cut the paper? Why does a car engine release so much heat? And why does a car engine make so much noise? It has to do with a very important concept: friction. Friction robs the machine of useful work. It robs the machine of useful energy. Friction converts some of the energy that you put into the machine, some of the work that you put into the machine, it converts it into heat and sound. And it never shows up as useful work. It's wasted. So here is an important thing to remember about any machine. All machines, no matter how big, no matter how small, no matter how simple, no matter how complicated, all machines lose some energy due to friction. And that energy shows as waste heat and waste sound, and only some of it comes out as useful work. This is where the concept of efficiency is important. Efficiency compares the work that goes into a machine with the useful work that comes out of the machine. The closer the useful work matches the work in, the closer those two are together, the more efficient a machine is. The higher the efficiency of the machine, the closer the work in is to the work out. And question 3 is a wonderful question because it really illustrates in a very visual manner exactly what efficiency is. And we could make this problem just as complicated as we wanted to. We could calculate the work in and the work out and calculate the efficiency of the ball, but we'd have to have the mass of the ball to do that, and we don't have that. But we can look at the work in and the work out as being relative to the heights to which the ball is dropped and bounces. So let's draw a diagram of this. Here we have a ball. It's at a height of 2.0 meters above the floor. There's the floor. If we drop this ball, the problem says it bounces back up only to 1.5 meters. And you notice that the distance of 0.5 meters is missing here. Where did it go? Stop and think about what the ball did. It fell to the floor, and as it fell, its gravitational potential energy was converted into kinetic energy, and when it hit the floor, what came out but some sound and also some heat. And it all wound up as heat in the environment. Well, that sound and heat that was lost is equal to the energy that represented by the half meter lost right here. That represents the energy that was lost. And so if we're going to calculate the efficiency, we don't really have to use, in this case, the energy or the work, because we don't have enough information to calculate it. All we have to do is look at the outcome of the situation. We started at 2 meters, it hit the floor, it only bounced back up to 1.5 meters. So the work in is the energy that went in right there, and we can use 2 meters for that. And the work out is represented by the 1.5 meters that we got back out of the ball. So that's going to be our work in and work out. Just like that. Now we can calculate the efficiency. The efficiency of the ball is equal to the work out over the work in. And the work out is represented by the height that the ball bounced up to after it hit the floor, which was 1.5 meters. And the work N is represented by the height of the ball that you see right here, 2 meters, the original height that was dropped from. And when we work this out and multiply it by 100%, we can calculate the efficiency of this ball. And when we calculate the efficiency of the ball, the efficiency works out to 75%. And think about this. We dropped the ball, it hit the floor, and it bounced back up to only 75% of its original height. You see, it started at 100% of its original height. It fell to the floor, lost some energy. How much? 25%. And it bounced back up to only 75% of its original height. Let me go through that again. We started at 100% of its energy. We dropped the ball from 2 meters. It falls down, it hits the floor, it loses 25% of its energy, its kinetic energy, as sound and heat. And when it bounces back up, it bounces back up only to 75% of its original height. Why? Again, because it lost 25% of that original energy that it started with. And so the efficiency of the rubber ball is 75%.